Hello, I'm Tom Robshaw. I'm a first year PhD researcher for the S.N.U.C.E.R group. This presentation is going to cover some of the work that I've been doing over the first 9 months of my PhD. So I'll start by taking a look at this unusual looking material here, which is called spent pot lining. What is it and why am I studying it? We'll then move on to look at fluorspar, calcium fluoride, why its recycling and recovery is important to our global economy, and how we feel that might be achieved by ion exchange technology. Finally, I'll share and discuss some of the results I've obtained so far. So, to answer the question of where spent pot lining, abbreviated to SPL, actually comes from, our journey really begins here within the primary aluminium smelting industry. So in this Hall-Héroult industrial scale electrolysis cell, we have alumina, Al2O3, dissolved in a bath of molten cryolite, sodium aluminium fluoride. The alumina is reduced to pure aluminium metal, and correspondingly the anode is oxidized to carbon dioxide and carbon monoxide, completing the redox chemistry. What we're going to zone in on though is this cathodic cell lining material here. Now the cathode bar is not in itself consumed in the electrolysis reaction. It does however become degraded over a period of time due to contamination seeping into it from these very harsh reaction conditions above. And when the contamination proceeds to such an extent that the quality of the aluminium metal produced begins to suffer, the cell is decommissioned and drained, and all of the contaminated cell lining material is excavated, becoming spent pot lining. This is a photo of what you would see if you were to take a slice down the middle of an exhausted Hall-Héroult cell. You can see the degraded cathode bar near the top of the image, and you can also clearly observe that the extent of contamination is such that it's passed all the way through the carbon and deep into the refractory brick material below. In fact, when the cathode bars are excavated, they only retain around 50% of their original carbon content. The rest is taken up by the contaminants. Now, SPL is a highly toxic and really rather dangerous type of waste, partly because of the elevated levels of fluorides and cyanides that we see here. It also, when contacted with water, can give off a mixture of potentially explosive gases. In fact, this quite infamously led to a cargo ship which was carrying some SPL waste across the ocean for disposal, actually exploding due to an accumulation of these gases within its hull. So clearly SPL presents a considerable safe storage challenge. But in fact, of the around about 1.3 million tonnes of SPL produced per year, we estimate that around 75% of this is either stored in secure repositories or simply dumped in unsecured landfill sites. Now clearly this is unacceptable from a cyclic economy perspective. But SPL should not just be seen as a dangerous waste, it's also a potential resource, and that's primarily because, again, of this high fluoride content here. The recycling and recovery of fluoride is absolutely paramount to our efforts to move towards a less wasteful, more cyclic kind of global economy. This is because we are rapidly depleting our natural reserves of fluorspar, calcium fluoride, and as you may well be aware, this mineral is the root of practically all industrially important fluorochemicals, such as, for example, the non-stick coating on saucepans, which many of us are familiar with. And there are a number of industrial strategies currently implemented to try and create these fluoride recycling loops that we so urgently require. Now, one of the more successful in recent years has been this hydrometallurgical system, in which you basically grind your SPL to a powder, and then leach it with hydroxide, creating an aqueous solution with all of the dissolved ionic contaminants that have come out of the SPL. We then add some steam to the system to evaporate off the water, and we're left with a precipitate of this sodium fluoride salt, from which we can ultimately derive our target product, which is calcium fluoride. Now, the step that we would look to zone in upon is this quite high energy evaporation process here. And we believe that this could potentially be replaced by an ion exchange step in which you use a selective sorbent to trap the fluoride that allows all of the other contaminants to pass through. So how would you go about creating a fluoride selective ion exchange resin? Well, one of the strategies you can look at is you can take a commercially available cation exchanger and you can preload it with a certain metal that is known to have high affinity for the fluoride ion. Well, that's exactly what we did with this widely available Purolite S950+. And our metal of choice for preloading was lanthanum. You can see in the diagram on the left the aminophosphonic acid functional group of the resin, and on the right you can see how the lanthanum ion coordinates to it. And this is what the resin looks like on a macroscopic scale. Each of these little beads is around 1/4 of a millimetre in diameter. Now, one of the questions that may have come to mind is, why did we choose lanthanum as our preloading metal? Well, there are several good reasons, in fact. Lanthanum belongs to a family of metals called the rare earths, although in itself it is in fact quite naturally abundant. Now, rare earths are mined together as a mixed ore, and the individual metals are then separated and purified. Some rare earths, such as neodymium, already have quite widespread industrial uses, and this is reflected in the market price of their oxides. In fact, neodymium oxide at the moment is worth around 30 times more than lanthanum oxide. So clearly there is some merit in trying to derive proper industrial uses for these, at present, more neglected members of the rare earths family. Now, obviously lanthanum can't compete with very common metals such as iron and aluminium in terms of cost, but in fact the potential for recycling and regenerating your ion exchange resin in such a system as we're proposing is quite significant. So you wouldn't actually have to buy as much lanthanum oxide in if you were looking to implement this ion exchange step as perhaps you might think. Anyway, back to the resin. So for an ion exchange resin to be considered fit for purpose, we have to prove that it has at least a reasonable capacity for the analyte of interest that you're trying to pull out of solution, fluoride in this case. The way we do this is actually very simple. So we have an aqueous solution of known fluoride concentration, but importantly to this we've also added some of the other common cations and anions that we believe through literature studies would be solubilized through the alkaline leaching of SPL. So as well as fluoride we have sulfate, carbonate, aluminium notably, and also iron, ammonium and potassium. We bring these two into contact with each other under controlled conditions for a defined period of time, and then we can analyse the solutions before and after contact with a fluoride ion selective electrode. From this we can derive an uptake capacity for the resin in units of milligrams of fluoride extracted per gram of resin. Let's look at some results. So this is a comparison of the performance of our resin with some other similarly modified ion exchanges that have been reported in the literature. So these researchers have used aluminium as their preloading metal, these lanthanum again, and these cerium, which is a close relation of lanthanum. Now it should be said at this point that the majority of the literature looks only at fluoride extraction from a simple sodium fluoride salt solution. So for the purposes of a fair comparison, we also looked at extraction from this matrix, represented by the green bar in the graph, as well as extraction from our emulant SPL leachate, which is the red bar. And what we can see from this is that not only does our resin outperform what was previously reported in the literature on a level playing field, but also, and more interestingly, we get this very considerable enhancement effect when we try to extract fluoride from the emulant SPL leachate. This is actually highly unusual behaviour because when previous researchers have added other anions and cations to the system, it's either had a negligible effect on the fluoride uptake, or it's actually decreased it because of other anions in the system competing with the fluoride for binding sites on the metal. What you'll never see is an enhancement effect, but that's precisely what we have here. So why should this be? Well, to start to try and answer that question, you can look at the kinetics of the two systems. So this graph shows the variation in the resin's fluoride uptake over a period of time. And what we see is that when we're extracting from the simple sodium fluoride solution, the uptake rises quickly and then gradually levels off and reaches an equilibrium, becoming almost constant. This is exactly the kind of pattern that you would expect to see from a system that is dominated by chemical bonding interactions, as ours is. In contrast, for the uptake from the emulant leachate, the uptake does not reach a steady state after the initial plateau. Rather, it continues to increase, and it seemingly does so in a number of discrete individual steps. Again, this is highly unusual. You will not see kinetic data such as this reported in the literature very often. So in subsequent studies, we began to vary the concentrations of the different components in the emulant leachate matrix. And by doing this, it was revealed that it was actually mainly the dissolved aluminium in the system, which, when present at a certain molar ratio, aluminium to fluoride, appeared to have this strongly activating effect on the resin's performance, which is what this graph shows here. We can then start to try and translate that to what's going on at an atomic level. It turns out there are actually 3 different uptake processes to consider here. The first 2 are very fast. One is the direct exchange of water and hydroxyl ligands for fluorides. There's also this secondary hydrogen bonding interaction between the aqueous fluoride ions and the unoccupied aminophosphonic acid coordination sites that do not have a lanthanum ion on them. How do we know this? Well, we can calculate an estimate for the number of lanthanum ions that are transferred onto a gram of resin during preloading. We can also calculate the number of fluoride ions that are taken up during contact. Now you can see from the diagram on the right that each lanthanum ion can only accommodate 3 fluoride ligands, otherwise the species formed is simply not chemically sensible. But it actually turns out that at peak capacity, the ratio of fluoride to lanthanum is far, far in excess of what can be explained by this. So it means the secondary H-bonding process must also be occurring. And indeed there are examples in the literature that shows us that such interactions do readily occur. So those 2 processes explain the initial shape of the kinetic graph. What we then think happens is that a second, much slower uptake process takes over, dominated by the aqueous aluminium. We think it starts to form bridging complexes with the surface of the resin, and as it does so, it draws more fluoride out of solution with it. Again, we've calculated an estimate for the number of moles of aluminium that are transferred onto the resin during contact, we know that the aluminium doesn't push the lanthanum off the resin, and there are nowhere near enough vacant coordination sites for this to explain the data. So the only logical conclusion is that individual layers of aluminium and fluoride complexation are forming on the surface of the resin beads. It turns out as well that we think we can actually visualize this. So these are electron microscopy images, and if you look at the image on the far right, which is the surface of a resin bead that's been exposed to a fluoride solution of high aluminium concentration, you can see, although it is faint, but there is a definite texture that is developed here, which is not present on either of the other two photographs. This, we believe, is the start of the aluminium and fluoride complexation. And this building up of individual layers would quite nicely explain the secondary stages of the kinetics graph that we observe for extraction from the emulant leachate. So it turns out that, quite by accident if we're being honest, the conditions that have been created by the emulant leachate have had this strongly activating effect on the performance of the resin. Now, this is not only very interesting chemically, but also it could have real potential in an applied context were we actually to set this resin to work for fluoride recovery in the aluminium industry. So the thoughts I would leave you with then are as follows. Firstly, we've seen that SPL represents a potential resource of considerable value in terms of its fluoride mineral content. Secondly, I hope I've demonstrated that the ion exchange treatment that we are proposing has considerable potential in an industrial context due to its efficiency and energy saving potential. And finally, the lanthanum modified resin that we've synthesized not only performs at the absolute top end of what's been reported in previous literature for fluoride extraction from simple salt solution, but also there is this highly unusual and hitherto unreported enhancement effect caused by the resin being used in conjunction with the emulant SPL leachate. So I'll just take a moment to acknowledge these contributors to my research, and thank you so much for listening.